Look up at the night sky, and what do you see? A scattering of stars, maybe a planet or two, but beyond that serene view lies a reality so vast, so incomprehensibly enormous, it defies everything familiar to us. The universe isn't just big, it's a sprawling, dynamic tapestry of structures so colossal they make galaxies look like specks of dust. We're talking about cosmic leviathans, superclusters that stretch hundreds of millions of light years, filaments of dark matter weaving through the emptiness like invisible threads, and voids so empty they could swallow entire galactic neighborhoods without a trace. These aren't just abstract ideas, they're the true scaffolding of existence, the hidden architecture shaping everything we know, and yet most of us have no idea these titans even exist. That's why today we're diving deep into 30 astonishing facts about the largest structures in the universe, formations so immense they challenge our understanding of space, time, and reality itself. Imagine standing at the edge of a single supercluster, a gravitational metropolis where thousands of galaxies orbit one another in an intricate dance lasting billions of years. Or picture the cosmic web, a spider's silk of matter connecting everything in the known universe, a network so vast it took light nearly the entire age of the cosmos just to traverse it. These aren't science fiction, they're real, they're out there, and they're waiting to reshape how you see the night sky forever. This journey isn't just about scale, it's about perspective. Every fact we uncover peels back another layer of the universe's grand design, revealing just how small we truly are and how much wonder is still left to explore. From the mysteries of dark matter's invisible grip to the unfathomable voids where galaxies dare not wander, we're about to embark on a voyage that stretches the limits of imagination. So let's begin, because the universe has stories to tell, and they're more incredible than anything we could have dreamed. Picture the universe not as a random splatter of galaxies, but as an intricate, interconnected masterpiece, a shimmering network so vast it makes every map we've ever made look like a child's scribble. This is the cosmic web, the largest known structure in existence, stretching across billions of light years like threads of dew-laced silk. Galaxies don't drift alone, they cluster along these filaments, pulled into dense knots where filaments intersect, leaving behind enormous empty voids darker and emptier than anything our minds can fathom. But here's what's truly mind-blowing: most of this web is invisible. The glowing galaxies we see, just the glitter sprinkled atop something far stranger. The real scaffolding of the cosmic web is woven from dark matter, that mysterious substance that neither emits nor reflects light yet exerts an unmistakable gravitational grip. Like the hidden roots of a forest, dark matter's tendrils dictate where galaxies grow, how they move, even how fast they spin. Without it, the universe wouldn't just look different, it wouldn't exist as we know it. And the scale, it's beyond human comprehension. A single filament can stretch for hundreds of millions of light years, a highway of matter so long that if you traveled at light speed, civilizations would rise and fall before you reached its end. These filaments aren't static, either they pulse with motion, as galaxies slide along them like beads on a string, drawn toward the densest nodes in a dance that's lasted over 13 billion years. Yet for all its grandeur, the cosmic web is fragile. Those cavernous voids between filaments, they're not just empty, they're actively hostile to structure. They're expansive forces tearing apart any wisp of gas or dust that dares to linger. It's a universe of contrasts, unimaginable density and crushing emptiness, tangled together in a balance so precise it feels almost designed. So the next time you gaze at the stars, remember, you're not just seeing pinpricks of light. You're glimpsing the outermost threads of a web so enormous, so ancient, that we're only beginning to trace its edges. And somewhere in that vast network, on an unremarkable strand, our galaxy spins, a single knot in the universe's grand tapestry. Deep within the cosmic web lurks a structure so colossal it shouldn't exist, the Hercules-Corona Borealis Great Wall. a staggering filament of galaxies stretching an almost unimaginable 10 billion light-years across the observable universe. To put that into perspective, if you could somehow traverse it at the speed of light, you'd spend twice the current age of Earth just crossing from one end to the other. This isn't just big, it's a cosmic anomaly, a glitch in the fabric of space-time that defies our fundamental understanding of how the universe organizes itself. How did we even find something so vast? The answer lies in the universe's most violent explosions, gamma-ray bursts. These fleeting, ultra-energetic flashes, often triggered by dying stars or colliding neutron stars, act like cosmic lighthouses, briefly illuminating distant corners of space. By mapping thousands of these bursts, astronomers noticed an eerie pattern, an unusually dense concentration spanning a region of sky near the constellations Hercules and Corona Borealis. What they'd stumbled upon wasn't just a cluster of galaxies, but a megastructure so immense it breaks the long-standing cosmological principle that the universe should look roughly the same no matter where you observe it from. And that's where the mystery deepens. According to our best models of the universe, structures shouldn't grow this large. The cosmic speed limit, the speed of light combined with the finite age of the universe, places a theoretical cap on how big gravity can assemble matter over 13.8 billion years. The Hercules-Corona Borealis Great Wall shatters that limit, stretching so far that even at the dawn of time, its ends couldn't have communicated with each other to coalesce into a single structure. It's like finding a sandcastle on Earth that's taller than Mount Everest. Physics says it shouldn't be possible, yet there it stands. Some theorists suggest wild explanations. Maybe it's not one structure but a chance alignment of multiple filaments, a cosmic illusion. Others whisper about exotic physics, primordial irregularities from the Big Bang itself, frozen into the universe's blueprint, but the most thrilling possibility, that we're seeing the first cracks in our understanding of cosmology, a hint that the universe's largest structures still hold secrets no equation has yet captured. One thing's certain, this galactic leviathan forces us to rethink the limits of scale. It's not just a wall of galaxies, it's a challenge, a cosmic dare written across the sky in gamma-ray fire, waiting for us to unravel its paradox. Even the Hercules-Corona Borealis Great Wall had to start somewhere, and its predecessor in the record books, the Sloan Great Wall, still stands as one of the most jaw-dropping discoveries in modern cosmology. Stretching an astonishing 1.4 billion light-years through the depths of space, this gargantuan ribbon of galaxies rewrote the rules of cosmic architecture when scientists first mapped it in 2003 using data from the Sloan Digital Sky Survey. Here's what makes it extraordinary. Before this discovery, astronomers assumed galaxy clusters and superclusters were the universe's ultimate building blocks. The Sloan Great Wall shattered that assumption. Imagine a river of galaxies so vast that if you could see it with the naked eye, it would span 35 times the width of the full moon in our sky, an unbroken chain of cosmic cities, each one home to billions of stars. But the real shock wasn't just its size, it was the way this structure clashed with our models of how the universe should evolve. According to the prevailing theories, matter in the early universe should have distributed itself relatively evenly, with only slight ripples in density left over from the Big Bang. Gravity would then amplify those ripples over billions of years, slowly pulling galaxies into modest clusters. The Sloan Great Wall defied that gentle timeline. Its sheer scale suggested gravity worked faster, or that the early universe's density fluctuations were far more dramatic than anyone predicted. It was like finding a skyscraper in the middle of a medieval village. The universe had somehow built this titanic structure far earlier than its blueprints allowed. And the discoveries kept coming. The wall isn't just long, it's dynamic. Galaxies along its length move in concert, tugged by the gravitational pull of a hidden heart, an ultra-dense region nicknamed the Great Attractor, lurking behind the Milky Way's dust clouds. This invisible anchor helps explain why the entire structure coheres instead of scattering like marbles on a table. Yet for all its grandeur, the Sloan Great Wall is also a lesson in cosmic humility. Its title as largest structure didn't last. Discoveries like the Hercules-Corona Borealis Great Wall soon dwarfed it. But that's the nature of exploration. Each time we map deeper into space, we find new layers of scale, each one pushing the boundaries of what we thought possible. The Sloan Great Wall didn't just challenge science. It reminded us that the universe always has another surprise waiting just beyond the edge of our current understanding. Just when we thought we'd mapped the cosmic neighborhood, astronomers in 2020 peeled back the Milky Way's dusty veil and uncovered a hidden colossus. Known as the South Pole Wall, this sprawling curtain of galaxies spans 1.4 billion light-years, lurking in the cosmic shadows directly behind our own galaxy. It's like standing in front of a mountain and suddenly realizing there's an entire mountain range concealed just beyond it, invisible only because we were too close to see it. What makes this discovery so groundbreaking isn't just its size, though it rivals the Sloan Great Wall, but the ingenious way scientists detected it. Normally, galaxies hiding behind the Milky Way's thick dust lanes are nearly impossible to observe with traditional telescopes. Instead, researchers turned to a cosmic proxy, galactic motion. By analyzing the subtle gravitational tugs on thousands of visible galaxies, they reconstructed the presence of this hidden behemoth, much like tracing the outline of a shadow in the dark. The result, a structure so vast it contains hundreds of thousands of galaxies, their collective gravity warping spacetime itself. But here's where it gets eerie. The South Pole Wall isn't just sitting quietly, it's pulling on us. Along with the Shapley supercluster and the Great Attractor, it's part of a gravitational tug of war influencing the motion of our entire local group of galaxies. Imagine floating in a river where unseen currents dictate your path. That's exactly what's happening to the Milky Way as these titanic structures drag us through the cosmos at over 600 kilometers per second. Yet the wall's discovery also raises profound questions. Why do such massive structures keep appearing exactly where our vantage point makes them hardest to see? It's a humbling reminder that even in an age of advanced telescopes, we're still mapping the universe with blind spots, and every time we eliminate one, the cosmos reveals another layer of its grand design. The South Pole Wall isn't just a structure, it's a signpost pointing to all the wonders still lurking in the unlit corners of our celestial map. We may think of our Milky Way as a grand cosmic island, but in reality, it's just one humble resident in a sprawling galactic metropolis known as the Laniakea supercluster. Encompassing over 100,000 galaxies across 520 million light-years, this vast structure redefines what home means on the grandest scales. The name itself, Laniakea, comes from the Hawaiian words for immeasurable heaven, and it couldn't be more fitting. Picture a celestial watershed where galaxies flow like rivers toward a common gravitational basin. At its heart lies the Great Attractor, an enigmatic region of space with the gravitational pull of tens of thousands of Milky Ways, drawing entire galaxy clusters toward it in a slow but inevitable cosmic migration. Our galaxy sits on the fringes of this supercluster, part of a neighborhood called the local group, which itself is just one small tributary in Laniakea's immense flow. What makes this discovery revolutionary is how it reshapes our cosmic map. Before Laniakea's identification in 2014, astronomers grouped galaxies based on simple proximity, creating arbitrary boundaries between superclusters. But by tracking the subtle motions of galaxies through space, their velocities and trajectories, researchers realized these cosmic cities weren't just neighbors. They were all bound together in a single, coherent structure. It's like realizing the towns you thought were independent are actually part of one vast nation, linked by unseen highways, and the scale is dizzying. If the Milky Way were the size of a grape, Laniakea would span the width of North America. Within its borders, galaxy clusters move in concert, following the gravitational contours of the cosmic web like leaves caught in a slow-motion whirlpool. Some regions are densely packed urban centers of galaxies, while others stretch into sparse galactic countryside. Yet even this titanic structure isn't the end of the story. Laniakea itself may be just a lobe of an even larger formation, hinting at layers of cosmic organization we're only beginning to trace. For now, though, it stands as our most complete address in the universe, a reminder that home isn't just our pale blue dot, but an entire archipelago of stars all drifting together through the darkness. Far beyond Laniakea's borders, in the constellation Centaurus, lies a gravitational juggernaut so powerful it bends the very flow of galaxies across intergalactic space, the Shapley supercluster. This staggering assembly of matter packs over 8,000 galaxies into a region just 650 million light-years away, making it the most massive concentration of mass in our cosmic neighborhood. But its true significance isn't just in its size, it's in the way this celestial titan reaches across the void with invisible gravitational fingers, tugging entire superclusters toward it like a cosmic puppet master. What makes Shapley extraordinary is its sheer density. While most superclusters resemble loose collections of galaxy clusters, Shapley's core is more like a crowded galactic metropolis during rush hour. At its heart sits a swarm of galaxy clusters so tightly packed that their mutual gravitational pull has accelerated them to velocities surpassing 2,000 kilometers per second. This isn't just a static structure, it's a dynamic, churning engine of gravity, actively reshaping the distribution of matter across hundreds of millions of light-years. Astronomers first pieced together its existence through meticulous observations of peculiar galactic motions. In the 1930s, Harlow Shapley noticed something odd. Galaxies weren't just drifting apart as the universe expanded, they showed strange, additional velocities that couldn't be explained by nearby mass alone. Decades later, we now understand this as the Shapley attraction, the gravitational pull of this distant supercluster, so immense it overrides even the expansion of space itself on local scales. Our own Milky Way, along with the entire Laniakea supercluster, is caught in this slow-motion current, being pulled toward Shapley at over 600 kilometers per second. Yet the most fascinating aspect might be what it reveals about cosmic evolution. Shapley represents a rare relic from the universe's more violent youth, when matter was clumping together with reckless abandon. Most structures of this density should have dispersed over time due to cosmic expansion, but Shapley's core remains intact, a testament to the overwhelming gravitational dominance at its heart. Some theorists speculate it may be the nucleus of an even larger structure we can't yet see, the visible tip of a cosmic iceberg whose full extent remains hidden by distance and dust. Standing in Shapley's shadow, figuratively speaking, forces us to confront an unsettling truth. For all our talk of superclusters and cosmic webs, we're still just beginning to map the true distribution of matter in the universe. Every time we think we've found the largest structure, something like Shapley reminds us that scale is relative, and the cosmos always has another surprise lurking just beyond the edge of our current understanding. While the Shapley supercluster pulls galaxies toward its dense core, another structure reveals how the universe stitches superclusters together into something even grander, the Pisces-Cetus supercluster complex. This sprawling network of galaxy filaments spans a staggering 1 billion light-years, weaving through space like the veins of some cosmic organism. Unlike isolated superclusters, this complex shows us the universe doesn't just build cities of galaxies, it builds entire countries with highways of matter connecting them across unfathomable distances. At its heart lies a revelation. What we once thought were separate superclusters, Perseus Pisces, Pegasus Pisces, and Cetus, are actually just dense knots in a single continuous web. Picture a mountain range where individual peaks blend into one another across the horizon. That's how these superclusters merge into a unified structure. Galaxies flow along its filaments like commuters on a cosmic freeway, pulled by gravity toward intersections where clusters collide in slow motion. One such junction, the Pisces-Perseus filament, stretches over 300 million light-years alone, a ribbon of galaxies so vast it could bridge the gap between Laniakea and Shapley 3 times over. The real magic lies in how this complex moves. Unlike static sculptures, these filaments vibrate with the echoes of ancient collisions. Astronomers tracing the motions of thousands of galaxies found something astonishing. Entire superclusters within Pisces Cetus are drifting together as if choreographed by some unseen hand. This isn't random, it's evidence of dark matter's hidden architecture, its gravitational scaffolding guiding the dance, yet the most humbling detail, we're inside it. The local group, and by extension our Milky Way, sits on the fringes of this billion-light-year tapestry. That means every star you've ever seen at night is just one thread in a weave so large we're still mapping its full extent, a reminder that even as we search for distant giants, we're already living within one. Hidden behind the Milky Way's dusty veil, where telescopes struggle to peer, lurks one of the universe's most baffling gravitational mysteries, the Great Attractor. This invisible behemoth exerts a pull so powerful it's dragging thousands of galaxies, including our own Milky Way, toward it at a mind-bending 14 million miles per hour. That's enough speed to circle Earth's equator in under 10 seconds. Yet despite its colossal influence, we've never directly seen it. The region it occupies lies in what astronomers call the zone of avoidance, a patch of sky obscured by our galaxy's own gas, dust, and stars, like trying to spot a mountain through a blizzard. So how do we know it's there? The evidence comes from the peculiar motions of galaxies. In the 1970s, astronomers noticed something unsettling. Every galaxy in our corner of the universe, from the local group to distant superclusters, was streaming toward the same unseen point in space, like leaves caught in a cosmic whirlpool. Calculations revealed the source had to be unimaginably massive, equivalent to tens of thousands of Milky Ways crammed into a region just 300 million light-years away. Yet when researchers pointed their telescopes in that direction, they found almost nothing. A few dim galaxies, but nowhere near enough visible matter to explain the gravitational tug. This sparked decades of detective work. Infrared and radio telescopes, which can pierce the Milky Way's dust, gradually unveiled hints. A dense cluster of galaxies called the Norma Cluster sits near the Great Attractor's heart, along with a sprawling confluence of superclusters. But even combined, their mass falls short of accounting for the observed pull. The leading theory: this region is just the visible tip of an even larger structure, perhaps a filament of the cosmic web so saturated with dark matter that its gravity dwarfs everything around it. What's truly humbling is realizing we're part of this cosmic current. Right now, the Milky Way is racing toward the Great Attractor, not because we'll ever reach it. The universe's expansion will likely prevent that, but because its gravity has set entire superclusters in motion like pieces on a chessboard. It's a reminder that even as we map the cosmos, some of its most powerful players remain hidden in plain sight, their presence betrayed only by the silent, relentless pull they exert on everything around them. And the mystery deepens. Recent observations suggest the Great Attractor itself may be moving, pulled toward something even more massive, the Shapley supercluster, over 600 million light-years away. If true, it means we're caught in a nested series of gravitational currents, each one flowing toward a larger cosmic drain. The Great Attractor isn't just a destination, it's a waypoint in a journey far grander than we'd ever imagined. If there's one place in the universe that embodies true nothingness, it's the Boötes Void, a yawning spherical chasm so empty it defies logic. Spanning 330 million light-years, this colossal region contains a mere 60 galaxies where astronomers expected to find at least 2,000. To put that in perspective, if the Milky Way were alone in a volume of space that size, its nearest neighbor would be over 80 million light-years away. The Boötes Void isn't just a gap. It's a cosmic desert so barren it makes the vast stretches between superclusters look like crowded city streets. How does something this empty even form? The leading theory suggests it's a fossil from the universe's infancy, a relic of extreme density fluctuations in the primordial plasma. Imagine the early cosmos as a pot of violently boiling water with bubbles forming and popping. The Boötes Void might be the footprint of an especially large bubble that expanded as the universe cooled, leaving behind a near-perfect vacuum when the surrounding matter collapsed into filaments and clusters. Some researchers propose an even wilder idea, that multiple smaller voids merged over billions of years like soap bubbles coalescing into one enormous cavity. But the void has secrets beyond its origin. The few galaxies trapped inside aren't just randomly scattered, they cluster along faint filamentary structures like survivors clinging to life rafts in an endless ocean. These galaxies show bizarre properties with higher rates of star formation and more youthful stellar populations than their counterparts in denser regions. It's as if isolation has forced them to evolve differently, turning the void into a natural laboratory for testing how environment shapes galactic evolution. Perhaps most unsettling is the way the Boötes Void challenges our assumptions. Standard cosmological models struggle to explain its sheer scale and emptiness, suggesting either rare statistical flukes or gaps in our understanding of large-scale structure formation. Some theorists speculate it could even be evidence of an ancient collision with another universe, a cosmic bruise left by something beyond our observable horizon. Gazing into the void forces a humbling realization. For all the universe's grandeur, its emptiest corners might hold the keys to its deepest mysteries. What looks like nothing is actually a whisper from the dawn of time, a silent echo waiting to rewrite our cosmic story. In the vast cosmic arena where size records are constantly shattered, a discovery in 2021 redefined what we thought possible. The giant arc, a structure so enormous it stretches disbelief to its breaking point. This colossal crescent of galaxies spans an incomprehensible 3.3 billion light-years, a distance so vast that light from one end wouldn't reach the other until long after our sun has burned out. Imagine a bridge so long it could connect the Milky Way to the edge of the observable universe not once but 30 times over. The giant arc isn't just big, it's a direct challenge to cosmology's foundational rules. Unearthed by painstaking analysis of quasar light absorbed by intervening gas clouds, this structure appears as a nearly symmetrical curve of galaxies, galaxy clusters, and intergalactic gas, tracing a shape roughly 1/15 the radius of the entire observable universe. Its scale violates the cosmological principle, the bedrock assumption that matter should distribute evenly across sufficiently large scales. At distances this immense, the universe should look homogeneous, no glaring patterns, no preferred directions. Yet here we are, staring at a galactic formation that resembles a cosmic smile etched across the sky, defying expectations with every billion light-year span. What makes this discovery so unsettling is the timing. The giant arc existed when the universe was barely half its current age, meaning gravity shouldn't have had enough time to organize matter on such a mind-boggling scale. It's like finding a fully formed city in what should be an untouched wilderness. A structure this coherent simply shouldn't exist so early in cosmic history. Some theorists suggest exotic explanations, primordial sound waves from the Big Bang frozen into the fabric of space, or wrinkles in space-time left by collisions with other universes in the multiverse. Others argue it might be a statistical fluke, a chance alignment of smaller structures that only appears connected from our vantage point. Yet the most tantalizing possibility is that we're glimpsing a deeper layer of cosmic architecture. Just as the Great Wall and Laniakea revealed larger structures than we'd imagined, the giant arc hints that the universe's organization operates on scales we're only beginning to perceive. Its galaxies aren't randomly placed, they follow the cosmic web's dark matter filaments, suggesting this arc might be a segment of some even grander pattern, a single brushstroke in a mural too vast to yet comprehend. For now, the giant arc stands as both revelation and riddle, a structure so immense it forces us to question whether the universe plays by rules we've yet to discover. And as telescopes grow more powerful, one thing becomes clear: the cosmos specializes in humility, forever showing us that what we call impossible is often just a prelude to the next great discovery. Just when we thought the universe couldn't possibly surprise us with larger structures, along comes the huge LQG, a gathering of quasars so vast it stretches nearly 4 billion light-years across the cosmos. That's longer than the distance from Earth to the farthest visible galaxies in the observable universe. Picture 73 of the brightest, most energetic objects in existence, each one a galaxy core blazing with the light of 1 trillion stars, arranged in a pattern so immense that it defies everything we know about cosmic structure formation. What makes this discovery so startling isn't just its size, it's the sheer audacity of its existence. Quasars are already cosmic anomalies, supermassive black holes at the centers of young galaxies, gobbling up matter so voraciously they outshine every star in their host galaxies combined. Finding them clustered together in such a tightly knit group shouldn't be possible. According to our best models of the universe, matter distributed by the Big Bang should have spread quasars relatively evenly, with no dramatic clumps on this scale. The huge LQG breaks that rule spectacularly, spanning a region of space so large that not even light could have crossed from one end to the other in the time since the universe began, meaning gravity wouldn't have had enough time to pull these objects together. Astronomers first spotted this behemoth by mapping the positions of quasars in the Sloan Digital Sky Survey, noticing an eerie concentration in the constellation Leo. The structure's name, Huge Large Quasar Group, barely does it justice. Unlike the cosmic web's delicate filaments, this is a blunt, almost crude aggregation of cosmic power, like finding a continent where we expected scattered islands. Some researchers argue it might not be a single structure at all, but a chance alignment of smaller groups seen from just the right angle. But the statistical odds of that are astronomically low, like rolling a die 1,000 times and getting the same number every single time. The real puzzle is what force could have orchestrated such a gathering. Current theories suggest unimaginably dense regions in the early universe's matter distribution, where gravity worked overtime to cluster quasars before the cosmos had fully expanded. Others propose more radical ideas: cosmic strings, defects in spacetime left over from the Big Bang, acting as gravitational scaffolds that funneled quasars into these impossible configurations. Whatever the explanation, the huge LQG stands as a glaring exception to our understanding of how the universe organizes itself, a cosmic splinter lodged in the smooth fabric of cosmological theory. Perhaps the most humbling realization: this structure existed 9 billion years ago, a snapshot of the universe in its rowdy adolescence. Which means right now, the light from its far side is only just reaching us, a message in a bottle from an era when the cosmos was half its current age, reminding us that the largest structures might not just defy our models, but our very conception of scale itself. Buried in the faint glow of the cosmic microwave background, the afterlight of the Big Bang itself, lies a cosmic anomaly so perplexing it might rewrite our understanding of reality. The CMB Cold Spot, a chilling void spanning nearly 2 billion light-years, isn't just colder than its surroundings. It's a ghostly fingerprint on the universe's oldest photograph, a region where the temperature plunges mysteriously below what any known physical process can explain. When astronomers first mapped the CMB's subtle temperature variations in 2003 using NASA's Wilkinson microwave anisotropy probe, this spot stood out like a frozen thumbprint. The rest of the sky showed tiny fluctuations, hotter and colder patches no larger than a few 100 million light-years, but the cold spot was different. Its temperature drop was 10 times more extreme than standard models predicted, and its size defied logic, a gaping cosmic hole so vast you could fit 30,000 Milky Ways end to end across it. Initial skepticism gave way to stunned realization this wasn't instrument error. It was real, so what could carve such a frigid abyss into the fabric of space-time? The leading theory points to an unfathomable void, a region so devoid of matter that photons from the early universe lost energy traversing it, a process called the integrated Sachs-Wolf effect. But here's the catch: even the emptiest known voids, like the Boötes Void, can't account for such an extreme temperature drop. The cold spot's sheer scale suggests something far stranger. Perhaps a supervoid of unprecedented emptiness, a cosmic desert spanning volumes we've never observed before. Then there's the radical alternative, a collision with another universe. Some theorists propose that the cold spot could be a bruise left by our universe grazing a neighboring bubble in the multiverse, a cosmic fender bender so violent it drained energy from that patch of space. While controversial, this idea hinges on quantum fluctuations during cosmic inflation, where adjacent universes might have left imprints on one another like fingerprints pressed into soft clay. Yet the cold spot refuses to surrender its secrets easily. Recent galaxy surveys revealed a surprising twist. Instead of finding an expected supervoid, the region contains a sparse but not entirely empty distribution of galaxies. This throws the void explanation into doubt, leaving astronomers scrambling. Could it be a statistical fluke, a 1 in 10,000 chance alignment of smaller cold patches? Or is it evidence of exotic physics, like a defect in spacetime's structure from the universe's first moments? What makes the cold spot truly mesmerizing isn't just its mystery, but what it represents: a crack in the smooth narrative of cosmology. For all our precision in mapping the universe, we're still stumbling across structures and phenomena that refuse to fit neatly into textbooks. It whispers a tantalizing possibility that the largest structures we've discovered so far might just be the visible edges of something far grander, something lurking beyond the current limits of our equations and telescopes. As we stare into this cosmic enigma, one thing becomes clear: the universe is still writing its rulebook, and every anomaly like the cold spot is a footnote begging us to read deeper. Whether it's a window into the multiverse or simply a reminder of how much we have yet to learn, this icy patch on the sky proves that even the oldest light in existence still has secrets to reveal. Galaxies aren't just drifting apart as the universe expands, they're being herded. In 2008, astronomers analyzing the motions of over 1,000 galaxy clusters stumbled upon something inexplicable. These massive structures were all streaming in the same direction at nearly 2 million miles per hour, as if dragged by some unseen force beyond the edge of our observable universe. They called it the dark flow, a cosmic current so vast it defies everything we know about the universe's structure. What makes this discovery so unsettling is its scale. The clusters involved span billions of light years, yet they move in eerie unison toward a region of space we can't even see, a place so distant its light hasn't had time to reach us since the Big Bang. Conventional cosmology says this shouldn't be possible. The universe's expansion should dilute gravitational influences over such distances, like ripples fading in a pond. Yet here we are, watching entire superclusters march in lockstep toward some hidden attractor. The leading theory, a mind-bending possibility: the dark flow might be evidence of structures outside our cosmic horizon. Imagine standing in a valley so vast you can't see the mountains on the other side, but you feel their gravity pulling you. Similarly, the flow could be caused by a supermassive concentration of matter, perhaps a hypercluster of galaxies or a titanic knot of dark matter, so enormous its gravity warps space-time across unfathomable distances. Some researchers speculate it might even be a remnant of quantum fluctuations from the universe's first moments, frozen into the fabric of reality before inflation stretched them beyond visibility. Skeptics argue it could be a statistical fluke or an artifact of incomplete data, but newer observations keep reinforcing the pattern. The Planck satellite's measurements of the cosmic microwave background added fuel to the fire, revealing subtle temperature shifts aligned with the flow, as if the universe's oldest light still carries whispers of this unseen pull. One thing's certain, the dark flow isn't just a curiosity, it's a crack in our cosmological models. If confirmed, it means the universe's largest structures might extend far beyond what we once thought was the edge, hinting at a reality where our observable cosmos is just one neighborhood in an impossibly vaster metropolis. And somewhere out there, beyond the reach of light itself, something massive is calling the shots. Before the Hercules-Corona Borealis Great Wall rewrote the record books, before Laniakea gave us a new cosmic address, there was CFA2, a quiet revolutionary that first cracked open our understanding of the universe's architecture. Discovered in 1989 by astronomers at the Harvard-Smithsonian Center for Astrophysics, this filament of galaxies stretched 500 million light-years across the northern sky like a faint scar in the fabric of space. At the time, it was the largest coherent structure ever identified, so immense that scientists initially doubted their own data. This wall wasn't just big, it was a philosophical earthquake. Before CFA2, most astronomers assumed matter in the universe was distributed fairly evenly, like flour scattered across a table. The idea that galaxies could cluster into organized patterns spanning hundreds of millions of light-years seemed absurd, like finding a mountain range taller than the distance between Earth and Jupiter. Yet there it was, a chain of galaxy clusters so vast you could line up 20 Milky Ways end to end, and still only span a fraction of its length. The discovery forced cosmology to confront an uncomfortable truth: the universe wasn't random. It had a skeleton. Mapping CFA2 was a feat of analog ingenuity. Without modern sky surveys or supercomputers, the team painstakingly plotted galaxy positions using photographic plates from telescopes, slowly revealing a pattern that resembled the branching veins of a leaf. What emerged wasn't a solid barrier, but a porous network where galaxies clung to intersecting filaments, leaving enormous bubbles of empty space between them. This was the cosmic web in its infancy, a blueprint for every supercluster we'd later discover. Yet the wall's legacy runs deeper than scale. Its existence directly contradicted the prevailing Swiss cheese model of the universe, which predicted matter should clump only on small scales. CFA2 proved gravity had been working overtime, sculpting structures far larger than physics said it could in the universe's lifetime. Some theorists scrambled to adjust their equations. Others proposed radical ideas like primordial magnetic fields or exotic dark matter behaviors to explain how such a colossus formed so quickly. Today, CFA2 might seem modest compared to later discoveries, but its impact is indelible. It taught us where to look, revealing that the universe's grandest designs often hide in plain sight, woven into the background of the sky. Every filament we've mapped since, from Sloan to Shapley, owes a debt to this unassuming wall of galaxies that first whispered a truth we're still unraveling. The cosmos builds bigger than we dare imagine. Tucked away in the constellation Pisces, hidden behind curtains of interstellar dust, lies a gravitational titan so massive it warps the very fabric of its cosmic neighborhood, the Saraswati supercluster. Named after the ancient Sanskrit goddess of knowledge and wisdom, this behemoth stretches 600 million light-years from end to end, a sprawling empire of 43 galaxy clusters collectively weighing 20 quadrillion times more than our Sun. To grasp that scale, imagine stacking every star in the Milky Way, not once but 4 million times over, and you'd still fall short of this structure's staggering mass. What makes Saraswati extraordinary isn't just its size, but its defiance of cosmic expectations. Discovered in 2017 by Indian astronomers combing through data from the Sloan Digital Sky Survey, this supercluster existed when the universe was barely 10 billion years old, far too young, according to standard models, for gravity to have assembled something so colossal. It's like finding a fully grown redwood tree in what should be a sapling-filled forest. The galaxy clusters within Saraswati aren't just neighbors, they're bound in an intricate gravitational dance, their motions revealing hidden highways of dark matter, weaving them together into a single, cohesive structure. But the real puzzle lies in Saraswati's location. It sits in a region cosmologists call the zone of avoidance, an area traditionally difficult to observe because our own Milky Way's dust and stars obscure the view. Cutting through this cosmic fog required infrared and radio telescopes, unveiling a supercluster so vast it influences the motions of galaxies millions of light years beyond its borders. Like a hidden mountain range redirecting continental weather patterns, Saraswati's gravity bends the trajectories of nearby galaxy clusters, sending them spiraling toward its dense core. Perhaps most intriguing is what Saraswati suggests about the universe's adolescence. Superclusters this massive are thought to be products of the modern cosmos, requiring nearly its entire lifespan to form. Finding one so well developed in the universe's relative youth implies either a flaw in our timeline or evidence of exotic physics at play. Some theorists propose that Saraswati might have formed atop a primordial, dark matter tsunami, a wave of ultra-dense material frozen into space during the Big Bang that jump-started galaxy formation. Others speculate it could be a rare cosmic coincidence, a chance alignment of smaller structures masquerading as a single entity. Yet staring at Saraswati's sprawling form, one truth becomes clear: the universe doesn't follow tidy rules. Just when we think we've mapped its limits, it unveils structures that rewrite the textbooks, forcing us to reconsider not just the scale of existence, but the very mechanisms that built it. And somewhere in that celestial labyrinth named for a goddess of wisdom, the cosmos seems to whisper a challenge: keep looking. The next great revelation might already be hiding in plain sight. Among the universe's most enigmatic giants, the Boötes Great Wall stands apart, not just for its staggering 1 billion light-year span, but for the profound paradox it presents. Discovered in 2016 by astronomers analyzing data from the Baryon Oscillation Spectroscopic Survey, this gargantuan structure is a chain of superclusters so vast it could bridge the distance from Earth to the farthest observable galaxies 10 times over. But here's the twist: its mere existence throws into question one of cosmology's most sacred principles, the idea that on large enough scales, the universe should look smooth and uniform. At first glance, the Boötes Great Wall resembles other cosmic titans, a filament of galaxies and galaxy clusters threading through the void like beads on an invisible string. But zoom out and its true nature emerges. This isn't just a random clump of matter. It's a meticulous arrangement where superclusters align with near mathematical precision, tracing a structure that dwarfs even Laniakea and the Saraswati supercluster combined. Mapping it required a revolutionary technique. Instead of just counting galaxies, scientists measured subtle ripples in the distribution of matter left over from sound waves in the infant universe, fossilized echoes of the Big Bang itself. These baryon acoustic oscillations revealed a pattern so coherent it defied expectations, like finding a perfectly straight road carved across a continent of chaos. Yet the real surprise wasn't the wall's size, it was what it implied about cosmic uniformity. According to the cosmological principle, the universe should appear roughly the same in all directions when viewed at scales beyond a few 100 million light-years. The Boötes Great Wall smashes that assumption to pieces. Its billion light-year length challenges the very definition of large-scale, suggesting that matter might organize itself into coherent structures far beyond what our models predicted. Some theorists argue it could be a statistical fluke, a cosmic mirage where smaller structures appear connected from our vantage point. But the odds of such a perfect alignment are astronomically slim, leaving scientists scrambling for alternatives. One compelling explanation lies in dark energy's influence. This mysterious force accelerating the universe's expansion might have sculpted the wall by suppressing the growth of structures in surrounding regions, effectively funneling matter into these sprawling cosmic rivers. Others propose even wilder ideas: primordial quantum fluctuations frozen into space-time during inflation, acting as blueprints for these impossible giants. What makes the Boötes Great Wall truly humbling is its silent defiance. It doesn't announce its presence with brilliant quasars or gravitational anomalies. It's a subtle overdensity, a whisper in the data that only reveals its grandeur under meticulous scrutiny. And that's the lesson here. The universe's largest structures might not always be the loudest. Sometimes they're hidden in plain sight, waiting for us to look at the cosmos not just with better telescopes, but with better questions. While most cosmic giants lurk in the northern skies, the southern hemisphere hides one of the universe's most overlooked titans, the Horologium Reticulum supercluster. Named after the constellations it spans, this sprawling web of galaxies packs a staggering 5,000 galaxy groups into a region stretching 550 million light-years. A cosmic metropolis so vast it could swallow the Laniakea supercluster whole and still have room to spare. What makes this structure remarkable isn't just its scale, it's the way it defies expectations. Unlike the neatly ordered filaments of the cosmic web, Horologium Reticulum is a chaotic jumble of galaxy clusters, subclusters, and loose groups tangled together in a gravitational embrace. Picture a bustling urban sprawl where galactic neighborhoods collide, their streets dark matter filaments crisscrossing in a frenzy. At its heart lies the Horologium cluster, a dense knot of galaxies so massive it acts like a gravitational anchor, pulling everything within hundreds of millions of light-years into its orbit. Discovering this supercluster was a triumph of persistence. Southern sky observations have long lagged behind the north due to telescope distribution and the Milky Way's obscuring disk. But in the late 1990s, redshift surveys began peeling back the veil, revealing a structure so immense it redefined our maps of the local universe. Unlike the Sloan Great Wall or Shapley supercluster, Horologium Reticulum isn't a neatly defined wall or sphere. It's a network, a three-dimensional labyrinth where galaxies thread through voids like pearls on a broken string. The real surprise came when astronomers studied its motion. This supercluster isn't static, it's flowing, caught in the gravitational current of something even larger. Like Laniakea's dance toward the great attractor, Horologium Reticulum's galaxies show a peculiar drift toward the so-called dipole repeller, a mysterious region of space so empty its repulsive force nudges entire superclusters away. It's a reminder that even structures of this scale are just pawns in a game of cosmic gravity we're only beginning to decode, yet the most intriguing detail might be its age. Many of Horologium Reticulum's galaxies appear older and redder than those in nearby superclusters, suggesting this region was one of the universe's earliest large-scale structures to form. Some clusters within it host galaxies that stopped forming stars billions of years ago, frozen in time like cosmic relics. This raises a tantalizing question. Did the supercluster's immense gravity somehow hasten galactic aging, or was it simply born in an era when the universe built things differently? Peering into Horologium Reticulum is like opening a window to the cosmos' formative years, a reminder that the southern sky isn't just a mirror of the north, but a realm where the universe writes its own rules in the language of ancient starlight. And somewhere in that tangled web of galaxies, the story of how structure itself emerged is still being told. Here's a startling truth about our cosmic address. We aren't just floating in the universe, we're floating in a void. The KBC void, named after astronomers Keenan, Barger, and Cowie, who identified it in 2013, is a staggering 2 billion light-year wide bubble of emptiness, and Earth sits right near its center. That means everything we see around us, the Milky Way, the local group, even the entire Laniakea supercluster, exists in one of the universe's loneliest neighborhoods, a relative desert surrounded by walls of galaxies so dense they bend the fabric of space itself. This isn't just a curiosity, it's a cosmic paradox. While most of the universe's matter clusters into filaments and superclusters, our corner of existence is oddly sparse. The KBC void contains about 20% less matter than the cosmic average, creating a gravitational oddity. Space inside this bubble expands slightly faster than the universe beyond its edges. Think of it like being in a slow-moving elevator while the rest of the building rushes upward at breakneck speed. This discrepancy isn't just academic, it might hold the key to one of cosmology's biggest headaches, the so-called Hubble tension, where measurements of the universe's expansion rate refuse to agree. How did we end up in such an empty pocket? The leading theory points back to the universe's infancy. Tiny quantum fluctuations in the primordial plasma may have left some regions slightly less dense, and over billions of years, those underdense areas ballooned into voids as gravity pulled matter toward denser regions like water draining from a bathtub. The KBC void's sheer size suggests it's not just a random fluctuation, it's a fossil from an era when the cosmos was still sculpting itself. But the most mind-bending implication is how this void distorts our view of the cosmos. When we peer out at distant supernova or galaxy clusters to measure the universe's expansion, we're seeing them from inside a gravitational anomaly. It's like trying to judge the ocean's tides while standing in a whirlpool. Our unusual location might be skewing the data, making the universe appear to expand faster locally than it truly does on larger scales. Yet the KBC void isn't just a scientific puzzle, it's a humbling reminder of cosmic perspective. For all our talk of superclusters and filaments, we're perched in one of the universe's quietest corners, gazing out at structures so immense they make our galactic home feel like a tiny outpost in an endless frontier. And somewhere beyond this bubble, the universe's true heartbeat thrums in the crowded streets of galaxy clusters we can only glimpse from afar. At the very dawn of cosmic structure, when the universe was a mere toddler just 2 billion years old, gravity was already hard at work assembling the first megalopolis of galaxies, the Hyperion proto-supercluster. Discovered in 2018 lurking in the constellation Sextans, this ancient behemoth holds the record as the earliest and most massive supercluster precursor ever found, a snapshot of the universe caught in the act of weaving its grand design. With a redshift of 2.45, we're seeing Hyperion as it appeared when the cosmos was only a fifth of its current age, a time when most matter still drifted in loose filaments rather than dense clusters. Yet here it was, already weighing in at a staggering billion suns, at 10,000 times the mass of our Milky Way, its gravitational pull drawing together nascent galaxies like iron filings to a magnet. What makes Hyperion so revelatory isn't just its age, but its structure. Unlike modern superclusters that resemble flattened chains or walls, Hyperion sprawls in 3 dimensions like a cosmic hedgehog, with at least 7 distinct filaments radiating outward from dense nodes where galaxy clusters were beginning to crystallize. Imagine a spiderweb still under construction, its threads pulled taut by the weight of dew droplets. That's how Hyperion's dark matter skeleton was already shaping the flow of gas and galaxies, setting the stage for the cosmic web we see today. These filaments aren't random. They align with predictions from supercomputer simulations of the early universe, offering the first observational proof that gravity began assembling large-scale structure far earlier than we'd dared hope. But the real shock came when astronomers calculated Hyperion's growth rate. At 2 billion years old, it was already as massive as some mature superclusters today, suggesting the early universe might have forged these titans through some forgotten recipe. One theory points to dark matter tsunamis, primordial waves of ultra-dense material left over from the Big Bang that jump-started galaxy formation in their crests. Another proposes that Hyperion sits at the intersection of multiple cosmic filaments, where matter funneled in from all directions like rivers merging into a lake. Either way, its existence forces us to reconsider how quickly gravity could work in the universe's youth, when conditions were radically different from the relatively sedate expansion we see now. Peering into Hyperion is like uncovering a fossilized blueprint, one that shows the universe didn't build its largest structures piece by piece, but in great coordinated bursts. The galaxies within it are younger, hotter, and more chaotic than their modern counterparts, blazing with star formation rates hundreds of times higher than anything in today's universe. It's a place where the rules were different, galactic collisions were constant, black holes feasted voraciously, and the first heavy elements were being forged in stellar furnaces at breakneck speed. Yet despite this frenzy, Hyperion's underlying architecture already mirrored the orderly patterns we see in contemporary superclusters, proof that the universe's grand design emerged not gradually, but in flashes of brilliance we're only beginning to decipher. This ancient giant whispers a tantalizing possibility that the largest structures we see today, from Laniakea to Shapley, might have been predetermined by seeds planted when the cosmos was still in its infancy. Hyperion isn't just a relic, it's a Rosetta Stone waiting to teach us how gravity wrote the first chapters in the story of everything. One of the most violent engines in the universe lies at the heart of Alcyonius, a galaxy so ordinary in visible light you'd glide right past it. But when viewed through radio telescopes, it transforms into the largest single structure ever discovered, twin jets of plasma stretching 16 million light-years from tip to tip. That's enough distance to thread the Milky Way and Andromeda together 50 times over with room to spare. This isn't just a galaxy, it's a cosmic particle accelerator turned up to 11. Its supermassive black hole launching jets so powerful they punch straight through intergalactic space like a pair of titanic searchlights, illuminating the darkness far beyond the galaxy's stellar borders. What makes Alcyonius so extraordinary isn't just its size, it's the sheer audacity of its existence. Most radio galaxies span a few million light-years at most, their jets eventually stalling as they plow into the surrounding intergalactic medium. But Alcyonius's jets refuse to quit. They stretch across a mind-numbing 5% of the entire observable universe's radius, a scale so vast it makes even the Hercules-Corona Borealis Great Wall look modest by comparison. And here's the twist, the galaxy at its center is utterly unremarkable, a sleepy elliptical galaxy with a black hole no more massive than those found in thousands of other galaxies. So how did it birth such a monstrosity? The secret lies in its environment. Alcyonius floats in a particularly sparse region of space, a cosmic backwater where the intergalactic gas is thinner than usual. With less resistance to push against, its jets could propagate farther than any we've seen before, like a ship sailing on calmer seas. But there's another possibility, one that sends chills down astronomers' spines. What if Alcyonius isn't special at all? What if there are countless galaxies like it, their jets stretching far beyond the limits of our detection, silently painting the cosmos with invisible brushstrokes of plasma? Peering into these jets is like reading a fossil record of the galaxy's violent past. The particles within them, accelerated to nearly light speed by the black hole's magnetic fields, trace a history of outbursts spanning tens of millions of years. Some regions glow brighter where the jet encountered denser gas, creating luminous knots like beads on a string. Others fade into whispering halos, the last remnants of eruptions that ceased long before the first mammals walked the earth. Yet the most humbling realization isn't Alcyonius's scale, it's our luck in finding it. Radio galaxies this large are so faint at their edges that they blend into the background noise of the universe. We only spotted this one because its orientation lines up perfectly with Earth, like staring down the barrel of a cosmic cannon. That raises an eerie question. How many more of these titans are out there, unseen and unmapped, their vast structures hidden in plain sight? Alcyonius doesn't just break records, it shatters assumptions. It forces us to reconsider how black holes interact with their surroundings, how energy propagates through the cosmic web, and perhaps most importantly, how much we still have left to discover. In a universe where even the quietest galaxies can unleash invisible giants, the message is clear: the cosmos always has another surprise up its sleeve. 7 billion light-years away, in the constellation Phoenix, two Galaxies clusters are committing the most spectacular act of cosmic violence ever witnessed, a collision so violent it warps the fabric of spacetime itself. Known as El Gordo, Spanish for the Fat One, this titanic structure is the most massive galaxy cluster ever discovered at such extreme distances, a behemoth weighing in at 3 quadrillion times the mass of our Sun. To grasp that scale, picture every star in the Milky Way multiplied by 15,000, then crammed into a region just 6 million light-years wide. What makes El Gordo truly extraordinary isn't just its size, but the way it formed. Hubble and Chandra telescope observations reveal it's actually two separate clusters caught mid-collision, their galaxies whipping past each other at millions of miles per hour while their superheated gas clouds slam together like tidal waves. The aftermath is written in X-rays. The shock wave from this cosmic pileup heats gas to 200 million degrees Fahrenheit, making it glow brighter than some quasars. Yet the real story lies in what we can't see. The cluster's ghostly halo of dark matter, mapped by the warping of background starlight, reveals these invisible tendrils outweigh the visible matter by a factor of 40 to 1. The violence doesn't stop there. When astronomers first measured El Gordo's redshift, they faced a paradox. The cluster's sheer mass seemed impossible for its age, a 7-billion-year-old relic from when the universe was half its current size. According to standard cosmology, gravity shouldn't have had enough time to assemble something so colossal so early. One theory suggests El Gordo was born in a rare overdense pocket of the early universe, where dark matter's pull jump-started galaxy formation like a cosmic fast-forward button. Others propose its titanic mass comes from kinetic energy, the unimaginable force of the collision itself temporarily amplifying its gravitational footprint, like a meteor's impact momentarily shaking the Earth more than its weight alone would suggest. But the most dazzling detail might be El Gordo's bullet-like substructure. As the clusters merge, their dark matter cores, revealed by gravitational lensing, have sailed ahead of the gas, creating a visible separation between matter and its invisible gravitational scaffolding. It's like watching a car crash where the passengers fly through the windshield while the engine lags behind. A phenomenon first seen in the nearby bullet cluster, but magnified here to staggering proportions. This separation is smoking gun evidence for dark matter's existence, proving it interacts differently than regular matter when cosmic giants collide. Yet for all its fury, El Gordo is also a time capsule. Its galaxies are older and redder than expected, with star formation that seemingly shut down early, as if the violence of the cluster's birth strangled new stellar generations in their cradle. Some astronomers speculate its central galaxies may already have merged into a single monstrous elliptical, a harbinger of what our own local group might become when Andromeda and the Milky Way collide billions of years from now. Peering at El Gordo is like catching a glimpse of the universe's most extreme construction sites, a place where gravity doesn't just build galaxies, but forges them in collisions of biblical scale. And somewhere in that distant cataclysm, amid the invisible dark matter and searing plasma, lies a humbling truth. The universe's largest structures aren't just static monuments. They're cosmic thunderclaps echoing across billions of years to remind us that even the mightiest giants are born from chaos. Deep in the constellation Phoenix, a cosmic furnace rages with unimaginable intensity. The Phoenix cluster, a galaxy cluster so extreme it redefines the limits of astrophysics. At its heart lies a supermassive black hole engaged in a paradoxical dance of destruction and creation. unleashing the most powerful outbursts ever witnessed while simultaneously heating its surroundings to temperatures rivaling the Big Bang itself. This isn't just a cluster, it's a pressure cooker of the cosmos where gas glows at billions of degrees and the very fabric of space crackles with energy. What sets the Phoenix cluster apart is its staggering central galaxy, home to a black hole that defies expectations. Most supermassive black holes in cluster cores alternate between periods of voracious feeding and quiet dormancy, but Phoenix's behemoth seems stuck in overdrive. It's devouring matter at a rate that should be impossible, swallowing the equivalent of 60 Earths every minute, while spewing jets of plasma so energetic they create shockwaves spanning hundreds of thousands of light years. These outbursts pump enough heat into the surrounding gas to prevent it from cooling and forming new stars, essentially putting the entire cluster's evolution on hold. Imagine a volcano erupting non-stop for millions of years. Its lava flows so vast they reshape the landscape of an entire continent. That's the scale of disruption we're witnessing. Yet the real wonder lies in the gas itself. Observations from the Chandra X-ray Observatory reveal a seething maelstrom of superheated plasma, reaching temperatures exceeding 100 million degrees hotter than the cores of some stars. This gas should have cooled over billions of years, collapsing inward to birth countless new stars. Instead, the black hole's relentless energy injections keep it perpetually simmering like a cosmic stovetop set to high. The result, a feedback loop of staggering proportions. As gas tries to cool, the black hole's outbursts reheat it, creating a self-regulating system that's both catastrophic and strangely elegant. But here's where it gets even stranger. Despite the chaos, the Phoenix cluster is also a factory of creation. Nestled within the turbulent gas, astronomers have spotted filaments of cooler matter, delicate tendrils condensing like dew on a spider's web. These filaments, some stretching for tens of thousands of light years, are the universe's stubborn defiance of entropy, pockets where nature fights back against the inferno to forge new stars. It's as if the cluster can't decide whether to destroy or create, caught in a tug of war between annihilation and rebirth. The implications ripple far beyond this single cluster. Phoenix challenges our understanding of how black holes shape their environments, proving they're not just destroyers but architects of cosmic ecosystems. Its extreme conditions mirror what theorists believe occurred in the universe's earliest clusters, when black holes and galaxies first began their intricate dance. By studying Phoenix, we're glimpsing a chapter of cosmic history written in plasma and gravity, one where the rules are stretched to their limits, and the universe reminds us it's always capable of one more surprise. Perhaps the most humbling lesson comes from the cluster's sheer persistence. The energy bill for heating gas on this scale is incomprehensible, equivalent to detonating 1 trillion nuclear bombs every second for billions of years. Yet the Phoenix cluster pays it without flinching, a testament to the raw power lurking in the hearts of galaxies. It's a vivid reminder that for all our theories and models, the universe still holds monsters we've only begun to understand, and sometimes the most extreme environments reveal the deepest truths. Just 320 million light-years from Earth, in the constellation Coma Berenices, lies one of the densest gatherings of matter in our cosmic neighborhood, the Coma Cluster. This bustling metropolis of over 1,000 galaxies packs the mass of 20,000 Milky Ways into a region only 20 million light-years wide, creating a gravitational maelstrom where galaxies whip past each other at thousands of kilometers per second. But what makes Coma truly historic isn't just its scale. It's the role this cluster played in unraveling one of the universe's greatest mysteries, the existence of dark matter. Back in the 1930s, astronomer Fritz Zwicky noticed something bizarre when studying Coma's galaxies. Their velocities were far too high for the cluster's visible mass to hold them together, like watching children on a merry-go-round spinning so fast they should fly off, yet somehow staying firmly seated. The math was undeniable. Coma needed 400 times more mass than its glowing stars and gas could account for, or its galaxies would have scattered into the void long ago. Zwicky's term for this missing mass, dunkel materie, dark matter. Though ignored for decades, his discovery in this unassuming cluster would eventually revolutionize cosmology. Peering into Coma today is like stepping into a gravitational funhouse. At its heart sit two colossal elliptical galaxies, NGC 4889 and NGC 4874, each over 10 times larger than the Milky Way. These brightest cluster galaxies act as anchors, their monstrous gravity shepherding thousands of smaller galaxies into chaotic orbits. Some spiral galaxies plunge through the cluster's core, their gas stripped away by the hurricane of hot plasma between galaxies, leaving behind orphaned stars adrift in intergalactic space. Others huddle in groups, their shapes distorted by tidal forces into long, shimmering streams, cosmic breadcrumbs marking the cluster's violent mergers over billions of years. Yet the real action happens in what we can't see. X-ray telescopes reveal Coma's true heart, a seething ocean of superheated gas reaching 50 million degrees Celsius, so dense it outshines all the cluster's stars combined. This gas isn't just a byproduct, it's a fossil record. As galaxies fall into the cluster, their own gas is ripped away and heated by the intergalactic medium, like leaves burning in a furnace. The energy released is so immense it creates shockwaves that ripple across millions of light years, redistributing matter in ways we're still deciphering. What makes Coma a living laboratory is its balance of chaos and order. Unlike younger, still-forming clusters, Coma has had time to settle into a rough equilibrium, its dark matter halo smoothing into a vast, invisible sphere while galaxies orbit like bees around a hive. Yet even here, surprises lurk. Recent studies found galaxies moving in coordinated flows, suggesting dark matter isn't just a static scaffold but a dynamic, ever-evolving framework that responds to the cluster's growth. Some galaxies even seem to be slingshotting off dark matter concentrations, their trajectories bending in ways that hint at substructures within the invisible halo. The legacy of the Coma cluster extends far beyond its borders. Every time astronomers study dark matter's fingerprints in galaxy rotations, cosmic microwave background patterns, or gravitational lensing, they're standing on the shoulders of Zwicky's work here. It reminds us that sometimes the universe's deepest secrets hide not in distant, exotic locales, but in plain sight, if only we know where to look. And for Coma, that truth resonates in every whirling galaxy, every wisp of stripped gas, and every invisible tug of the dark matter that binds them all together. Imagine two massive cities made of galaxies slamming into each other at unfathomable speeds. That's the Bullet Cluster, a cosmic collision so extreme it handed scientists the smoking gun in the hunt for dark matter. Located 3.8 billion light-years away in the constellation Carina, this system isn't just a pair of galaxy clusters crashing together. It's a living experiment revealing secrets about the invisible scaffolding that holds the universe together. When these clusters collided, something extraordinary happened. The galaxies themselves, each containing billions of stars, passed right through one another like ghosts, barely affected by the encounter. But the hot gas between them, a superheated plasma detectable by X-ray telescopes, smashed together violently, creating a shock wave that glows brighter than a billion suns. That alone would make this system fascinating, but the real magic lies in what happened to the cluster's gravity. Using gravitational lensing, the way massive objects bend light from background galaxies, astronomers mapped where the bulk of the mass actually was. And here's the twist: the gravity wasn't centered on the glowing gas or even the galaxies. It was somewhere else entirely. That mismatch between visible matter and gravitational influence was the clearest evidence yet for dark matter. The Bullet Cluster showed us that while the gas ordinary, visible matter got stuck in the cosmic traffic jam of the collision, the invisible dark matter sailed straight through, completely unaffected. It was as if two crowds of people ran into each other, but their shadows kept moving forward on their own, untethered from the bodies casting them. This wasn't just theoretical physics anymore, it was proof written across the sky. What makes this discovery so groundbreaking is how elegantly it sidesteps decades of debate. Before the Boötes cluster, dark matter's existence was inferred from galaxy rotations and cosmic expansion, leaving room for alternative theories. But here, the separation was visible. The dark matter's gravitational fingerprint appeared in one place, the gas in another, and no tweak of existing physics could explain it away. Even now, it remains one of the most direct confirmations that most of the universe's matter doesn't interact with light at all. It's a hidden ocean we've only just begun to navigate. Yet the Boötes cluster isn't just about dark matter. It's also a masterclass in cosmic violence. The collision released enough energy to reshape the surrounding void, sending ripples through space-time itself. The Boötes in its name comes from the bullet-shaped shock wave in the gas, a remnant of one cluster punching through the other at millions of miles per hour. That shock, imaged by the Chandra X-ray Observatory, shows physics pushed to its limits, a natural particle accelerator where magnetic fields and turbulence whip charged particles to energies we can't replicate on Earth. And then there's the aftermath. Galaxies in the Boötes cluster now drift in a new configuration, their paths altered by the encounter, while the dark matter halos, still stubbornly invisible, continue their journey as if nothing happened. It's a snapshot of cosmic evolution in action, a reminder that even the largest structures are constantly changing, rearranged by forces both seen and unseen. Perhaps the most humbling lesson comes from the cluster's sheer resilience. A collision of this scale should have torn galaxies apart, yet they emerged mostly unscathed. It's a testament to how empty space truly is. Galaxies are like handfuls of sand thrown across a football field, so sparse that even in a head-on crash, actual impacts are rare. The real action happens in the spaces between, where gas, dark matter, and gravity weave a story far stranger than fiction. The Boötes cluster didn't just confirm dark matter, it gave us a front-row seat to the universe's hidden mechanics. And somewhere in that chaos of colliding giants, we caught a fleeting glimpse of the rules that govern everything. While Laniakea redefined our cosmic address, it's actually nested within an even larger galactic neighborhood, the Virgo supercluster, a sprawling metropolis of galaxies spanning 110 million light-years. Picture a web where each strand contains thousands of galaxies, all gravitationally bound in an intricate dance older than Earth itself. At its heart sits the Virgo cluster, a dense urban core packed with over 2,000 galaxies, while smaller groups like our local group orbit this gravitational hub like distant suburbs circling a bustling downtown. What makes this supercluster remarkable isn't just its scale, it's the delicate balance of forces holding it together. The Virgo cluster's immense gravity, equivalent to a quadrillion suns, exerts a pull so strong it's slowing down nearby galaxy groups, including our own. Right now, the Milky Way is falling toward Virgo at 300 kilometers per second, caught in a slow-motion plunge that began before dinosaurs walked the Earth. Yet we'll never crash into its core. The universe's expansion counteracts this pull, leaving us forever in orbit around this distant giant, a celestial dance where no partner ever touches. Peering into the Virgo supercluster reveals a cosmic fossil record. Its galaxies tell stories of violent mergers and quiet evolutions, with ancient ellipticals crowding the center and younger spirals like our Milky Way lingering on the fringes. Some galaxies trail streams of stolen stars, evidence of past collisions, while others float in near isolation, untouched for billions of years. This diversity isn't random, it's a direct result of environment. Galaxies near the supercluster's dense core are stripped of gas by relentless collisions, leaving them barren and red, while those on the outskirts retain the raw materials to birth new stars in brilliant blue spirals. Yet the most fascinating aspect might be its impermanence. Superclusters like Virgo are fleeting structures in cosmic time. As dark energy accelerates the universe's expansion, these gravitational networks will gradually unravel. Billions of years from now, the threads binding Virgo's galaxies will stretch and snap, its majestic web dissolving into the void. For now, though, it stands as a reminder. Our galaxy isn't just an island in space, but part of a vast, dynamic community whose rhythms shape everything from star formation to the very trajectory of our cosmic future. 65 million light-years away, practically our cosmic backyard, the Fornax cluster offers a front-row seat to one of the universe's most dramatic transformations. Unlike the chaos of the Coma cluster or the violent mergers of El Gordo, Fornax presents a quieter, yet equally revealing, laboratory for understanding how galaxies evolve under pressure. Here, hundreds of galaxies orbit a dense central core, their fates shaped by forces both seen and unseen, in a slow-motion ballet that's been unfolding since the age of dinosaurs. At first glance, Fornax seems unremarkable. Its brightest members, like the giant elliptical galaxy NGC 1399, don't blaze with the raw intensity of quasars or starburst galaxies. But that's precisely what makes it invaluable. Fornax is a middle-aged cluster, past the turbulence of youth but not yet settled into the monotony of old age. Its galaxies exist in a Goldilocks zone, dense enough to show the effects of their environment, but not so crowded that their individual stories get lost in the noise. Take NGC 1365, a spiral galaxy being slowly stripped of its gas as it plows through the cluster's hot intergalactic medium. Like a tree losing leaves in a storm, its star-forming material is being ripped away, destined to fade into a red, lifeless elliptical over billions of years. This process, called ram pressure stripping, is written across Fornax in exquisite detail, offering a preview of what might someday happen to our own Milky Way when it merges with Andromeda's future supercluster. Yet Fornax's real magic lies in its dark secrets. The cluster contains a puzzling surplus of ultra-compact dwarf galaxies, tiny but incredibly dense collections of stars that defy classification. Some may be the stripped cores of once larger galaxies, while others could be surviving relics from the universe's first wave of star formation. Their presence hints at a hidden history of cannibalism and survival, where small galaxies were devoured by larger ones, leaving only their indestructible hearts behind. What makes Fornax truly special is its role as a cosmic time capsule. Because it's relatively nearby, telescopes can resolve individual stars within its galaxies, turning abstract theories into observable reality. Hubble images reveal globular clusters, ancient stellar cities being torn from their host galaxies by tidal forces, their stars scattering into the cluster's halo like marbles spilled across a floor. Meanwhile, the Chandra X-ray Observatory maps the superheated gas between galaxies, showing how these invisible currents redistribute energy and matter on scales dwarfing anything in our solar system. For astronomers, Fornax is more than just a cluster, it's a bridge. Its moderate density mirrors conditions in the early universe when galaxies first began gathering into groups. By studying how its members interact today, we can piece together how the universe built its first large-scale structures, one galactic encounter at a time. And somewhere in its quiet orbits and fading spirals, we catch a glimpse of our own galactic neighborhood's future, a reminder that even the stars are subject to the pull of their environment, slowly shaped by forces older than time itself. Rising like a titan over the northern celestial sphere, the Perseus-Pisces supercluster weaves a tapestry of galaxies spanning 300 million light-years, a river of starlight flowing through the constellations it's named after. This gargantuan chain of galaxy clusters isn't just a random scattering, it's one of the most dominant features in our cosmic neighborhood, a gravitational nexus where thousands of galaxies orbit one another in a dance older than Earth itself. At its heart lies the Perseus cluster, a dense urban core of galaxies so massive that its gravity bends the light of objects behind it, creating natural telescopes that magnify the distant universe for astronomers. What makes Perseus Pisces extraordinary isn't just its size, it's the sheer density of its signature cluster. The Perseus cluster alone contains thousands of galaxies swimming in a sea of superheated gas at 60 million degrees, emitting X-rays so intense they outshine the combined light of all its stars. Nestled within this inferno is one of the universe's most haunting sounds, a supermassive black hole at the cluster's center, humming a note 57 octaves below middle C. A pressure wave resonating through the surrounding gas like a cosmic bass note that's been sustained for 2.5 billion years. But Perseus Pisces isn't just about raw power, it's also a time capsule. Many of its galaxies are ancient ellipticals, their star-forming gas stripped away eons ago by the cluster's harsh environment. Others, like the famous spiral NGC 1277, cling to their structure despite the gravitational turmoil, their arms studded with newborn stars defiantly glowing blue against the redder, aging galaxies around them. This diversity tells a story of survival. Some galaxies thrive in the supercluster's bustling core, while others linger on the quieter outskirts, their evolution slowed by the relative peace of cosmic suburbia. The supercluster's true brilliance lies in its role as a counterweight to our local cosmic landscape. While Laniakea and the Great Attractor pull us in one direction, Perseus Pisces exerts its own gravitational influence, its mass helping to shape the large-scale flow of galaxies across hundreds of millions of light-years. It's part of a vast cosmic tug-of-war, a reminder that even structures this immense are still subject to the pull of something larger, perhaps a filament of the cosmic web we've yet to fully map. Yet for all its grandeur, Perseus Pisces holds a quiet mystery. Recent surveys suggest it might be connected to the more distant Pisces-Cetus supercluster complex via faint filaments of galaxies, hinting at a structure so vast it could redefine our understanding of this celestial neighborhood. Like tracing the outline of a mountain range only to realize it's part of an entire continent, each new observation peels back another layer, revealing just how much we've yet to explore in what we once considered our own backyard. Gazing toward Perseus and Pisces, we're not just looking at a distant structure, we're witnessing a gravitational anchor, a cornerstone of the universe's architecture whose influence stretches far beyond the glittering galaxies we can see. It's a testament to the fact that even in the vastness of space, everything is connected, bound by forces that sculpt the cosmos on scales too grand to comprehend but too beautiful to ignore. Deep in the constellation Ophiuchus, astronomers have uncovered the aftermath of a detonation so powerful it makes supernova look like firecrackers. The Ophiuchus supercluster eruption, a cataclysmic outburst that carved out a cavity in space 15 times wider than our entire Milky Way. This isn't just an explosion, it's a cosmic-scale demolition project, the single largest release of energy we've detected since the universe's fiery birth. The culprit, a supermassive black hole gone rogue, unleashing a jet of plasma so intense it blasted through intergalactic space like a celestial blowtorch, leaving behind a scar visible across hundreds of millions of light years. What makes this event truly staggering is the raw power involved. The eruption released 5 times more energy than the previous record holder, enough to boil away every ocean on every planet in a galaxy 100 times over. To put that in perspective, the explosion's total output equals the energy the Sun will produce over its entire 10 billion-year lifespan, multiplied by 10 billion. All that fury originated from a single black hole's outburst, proving these gravitational monsters don't just consume matter, they can reshape entire superclusters when they unleash their wrath. The discovery came not through visible light but via faint X-ray echoes. The Chandra Observatory detected bizarre, concave edges in the supercluster's hot gas, a telltale sign of something punching outward with unimaginable force. These cavities, now filled with quieter radio emissions, trace the shockwave's path like smoke rings from a cosmic cannon. What's astonishing is how long this violence hid in plain sight. The eruption likely occurred hundreds of millions of years ago, its light taking eons to reach us, yet its impact remains etched into the fabric of space like a fossilized scream. But the real mystery lies in the black hole's behavior. Most active galactic nuclei erupt in cycles, feeding frenzies followed by quiet periods. The Ophiuchus event suggests some black holes might store energy for unprecedented durations before detonating in single apocalyptic bursts. Imagine a volcano gathering pressure for millennia, then erupting with enough force to vaporize continents. That's the scale of delayed fury we're witnessing. This explosion does more than break records, it rewrites what we thought possible. Structures this immense shouldn't exist in modern cosmology, where the universe's expansion dampens extreme events. Yet here it is, a testament to the fact that even in the universe's quieter epochs, its hidden engines can still unleash hell on scales that defy comprehension. The Ophiuchus superclusters scar isn't just a wound, it's a warning written across the sky in letters of fire and plasma, reminding us that the cosmos always keeps one final trump card up its sleeve. Among all the titans we've explored, none compares to the ultimate cosmic structure, the Hubble volume, our observable universe. This vast sphere, stretching 93 billion light-years in diameter, represents the maximum distance light could have traveled since the Big Bang, a frontier set not by space itself, but by the finite speed of light and the accelerating expansion of the cosmos. Within this bubble lies everything we can possibly study, at least 2 trillion galaxies, each a sprawling island of stars drifting in the dark, their light just now reaching us after eons of travel across the void. What makes this volume extraordinary isn't just its scale, it's that every point in the universe has its own Hubble volume, its own observable horizon. We're not at the center, we're simply trapped in our own light cone, a perspective that shifts with every passing moment. The galaxies near this theoretical edge appear frozen in time, their light so stretched by cosmic expansion that it arrives as faint whispers of radio waves carrying snapshots of the universe's infancy. Meanwhile, regions beyond this boundary remain forever invisible, their light still en route or already carried away by expansion faster than it can reach us, a cosmic event horizon hiding untold wonders. Consider the raw numbers. If each of those 2 trillion galaxies hosted just 100 billion stars, a conservative estimate, the observable universe would contain more stars than grains of sand on every beach and desert on Earth combined. Yet staggeringly, this entire colossal inventory, every quasar, supercluster, and swirling nebula, accounts for less than 5% of the universe's total content. The rest, dark matter sculpting the cosmic web, and dark energy relentlessly stretching space itself, ensuring that much of creation will forever lie beyond our view. The Hubble volume isn't static. Each second, expansion pushes hundreds more galaxies beyond our observational limit, their light fading like ships vanishing over the horizon. Telescopes like Hubble and JWST capture these fleeing photons, desperate to document as much as possible before the accelerating universe erases them from our sky. Already, we've lost sight of countless galaxies that were visible to our theoretical ancestors just 10 billion years ago. Their light now too redshifted or diluted to detect, their existence inferred only by the gravitational shadows they cast on the cosmic microwave background. This reveals the Hubble volume's cruel irony. The more we learn, the more we realize how much lies forever out of reach. Structures larger than this volume, if they exist, would be unknowable by any method, their existence relegated to speculation. Even within our observable bubble, we're only now grasping the true scale of formations like the Hercules-Corona Borealis Great Wall, which may stretch so far it challenges the cosmological principle itself. Yet for all its limitations, the Hubble volume remains our grandest classroom. Every photon that reaches us carries forensic evidence of the universe's history, from the first star's ignition to the last gasp of colliding galaxy clusters. It's a time machine where distance equals antiquity, letting us watch cosmic evolution unfold in real time if only we decode the light correctly. And somewhere in that vast archive of photons, spanning 93 billion light-years in every direction, lies the answer to humanity's oldest question: how did all this come to be? The Hubble volume doesn't just contain the universe, it contains every clue we'll ever have to understand it. After exploring titans like the Hercules-Corona Borealis Great Wall and the cosmic web, we reach a startling cosmic irony. The universe's grandest designs eventually dissolve into uniformity. Astronomers call this threshold the end of greatness, the scale beyond roughly 300 million light-years where the cosmos stops building recognizable structures and instead becomes a vast, featureless expanse. It's as if we've been studying the intricate brushstrokes of a painting, only to step back and realize the entire canvas is a single, uniform color. This transition isn't just philosophical, it's baked into the universe's blueprint. When you average matter distribution across these enormous scales, the dense superclusters and cavernous voids balance out, leaving no discernible pattern. Imagine zooming out on a mountain range until individual peaks blur into a flat horizon. That's what happens when we map galaxies across billions of light-years. The clumps and filaments so vivid in our local universe smear into homogeneity, like stirring cream into coffee until no streaks remain. But how do we know this isn't just a limitation of our telescopes? The evidence comes from two powerhouse observations: galaxy redshift surveys and the cosmic microwave background. By cataloging millions of galaxies, projects like the Sloan Digital Sky Survey revealed that while structures dominate at small scales a few hundred million light-years, their statistical distribution smooths out beyond that. Even more telling, the CMB, the universe's baby picture, shows temperature variations of just 1 part in 100,000, proof that matter was distributed with near-perfect uniformity in the early cosmos. Gravity then spent billions of years amplifying those tiny wrinkles into the web we see today, but the original smoothness still wins out at the grandest scales. This discovery isn't just academic, it reshaped cosmology. The end of greatness validates the cosmological principle, the foundational idea that the universe has no special place. No matter where you stand, the view on these scales should look essentially identical, a democratic fairness woven into space-time itself. It's why astronomers weren't shocked to find our Milky Way floating in the KBC void. Even an unusually sparse region like ours is just a tiny fluctuation in the overall uniformity. Yet the real magic lies in what this transition implies about dark energy. As the universe expands, this mysterious force not only stretches space but actively works to erase structure. On small scales, gravity fights back, binding galaxies and clusters together. But beyond the end of greatness, dark energy wins, its relentless push overwhelming gravity's pull. In time, even the Hercules-Corona Borealis Great Wall will be diluted, its galaxies scattered like dust in the wind. So where does that leave our search for cosmic titans? The end of greatness isn't a wall, it's a horizon of comprehension, reminding us that the universe's true architecture transcends what we can classify. Those filaments and voids aren't illusions, they're real features, just as waves are real even though the ocean, viewed from space, appears smooth. The difference is perspective. And somehow, that's the most profound lesson of all: the universe's grandeur doesn't disappear when we zoom out. It simply changes form, trading visible complexity for a deeper, more subtle order, one we're only beginning to trace. From cosmic megastructures stretching billions of light-years to voids so empty they defy logic, our journey through the universe's largest formations has been a masterclass in perspective. We've stood at the edge of superclusters where galaxies swarm like fireflies, traced filaments of dark matter weaving the cosmos together, and stared into abysses so vast they could swallow entire galactic neighborhoods without a trace. These aren't just abstract curiosities, they're the scaffolding of reality itself, forcing us to confront how small we truly are in a universe that builds on scales beyond human comprehension. Think back to the Hercules-Corona Borealis Great Wall, a structure so enormous it breaks the rules of cosmic evolution, or the eerie dark flow, dragging galaxies toward something beyond the visible universe. Remember the Boötes Void, where 60 lonely galaxies drift in a sea of nothingness, and the Phoenix Cluster, a celestial furnace where black holes sculpt entire ecosystems. Each discovery peels back another layer of the universe's grand design, revealing how much we've yet to learn and how often our assumptions shatter against the rocks of observation. What's truly humbling isn't just the scale, but what these giants tell us about our place in the cosmos. We're not just perched on a pale blue dot, we're floating in the KBC Void, one of the universe's loneliest neighborhoods, while hurtling toward the great attractor at millions of miles per hour. Even Laniakea, our home supercluster, is but a single thread in the cosmic web's unimaginable tapestry. These aren't just facts, they're invitations to wonder, to reassess what it means to exist in a universe where large is redefined with every new telescope pointed at the sky. Now it's your turn. Which of these cosmic titans left you awestruck? Was it the giant ark's impossible symmetry, or Alcyonius's radio jets stretching far beyond any galaxy's domain? Maybe Saraswati's ancient sprawl, or the Ophiuchus explosion's apocalyptic fury? Drop your pick in the comments, because the universe's greatest marvels aren't just for scientists to ponder. They're for all of us to share, debate, and use as springboards for the next big question. After all, every time we map these giants, we're not just charting space, we're drawing a fuller, richer portrait of home.